Hello everyone, my name is Shin and I'm majoring electrical engineering and also studying future vehicle convergence engineering under the RISE program. This project started from a simple question of curiosity. While studying motor design in my lab, I realized that most high-speed motors are made of heavy steel or silicon cores. They perform well, but they're expensive and hard to modify in shape. As an engineering student, I always ask myself how we can make motors lighter, cheaper, and more efficient. One day I came across an article about 3D printing ferromagnetic materials, and I started to wonder, what if we make a motor not from metal, but from 3D printed materials? That idea became the beginning of this research, a combination of curiosity, design, and engineering logic. Before designing, I studied different 3D printing filaments. Among them, one material caught my attention. This magnetic iron PLA, which is protopasta, is a PLA-based plastic mixed with finer iron powder. It's ferromagnetic, meaning it reacts to magnetics and is printable with an ordinary FDM printer. From datasets and papers, I found these properties 1.5 times the density of standard PAA, and magnetic saturation is about 0.15 Tesla, and relative permeability is between 5 and 8. Thermally, it softens around 55 degrees and melts at 155 degrees. This low temperature shows why heat is the biggest challenge when using 3D printed materials. However, I also discovered something important. A 2023 IE and 2020 ICIRA's paper indicated that even though this material could form a working motor, the magnetic flux was only 1.6 Gauss per pole, which is almost 10,000 times weaker than in normal steel motors. That made me think maybe the material is too weak, but what if we test it more deeply? Can we still make it functional if we understand its limits? I designed the 6-slot 8-pole outer rotor BFEC motor using Cryo 4. I chose the outer rotor configuration to boost the torque, compensating for the PLA's weak flux. The 6-pole 8-slot combination minimizes corking torque, helping with 3D printing precision issues. The image here shows the assembly I made, including the stator, rotor, and air gap of about 1.2 millimeters. After that, I wanted to analyze the thermal behavior because this material also has a low softening temperature. I built a thermal model using MATLAB and Python based on the loomed parameter thermal network concept. As shown in the Simscape diagram on the screen, each part was modeled as a thermal node with its own resistance and heat capacity. The system followed this equation, and this summarizes the function of the thermal blocks used. I first implemented this model using MATLAB Simscape, but the output showed a slightly distorted shape. Then I processed the loss data in MATLAB. I used the pre-computed loss values from the reference dataset. As shown in the top graph, the heat flow was accurately reconstructed, which allow us to confirm the load pattern for the next step. Then I recreated the same model in Python using a Euler numerical method to update temperatures over time. And this loop continuously calculates heat balance at every time step. As you can see in this temperature graph, the temperature keeps rising over time instead of converging. This means heat generation is higher than heat dissipation. Around the early stage, the temperature already exceeds 55 degrees and later even passes melting point, meaning the parent structure will fail every early in real operation. However, when I simulate the same model with an aluminum or carbon fiber PLA case, as shown in this graph, the peak temperature dropped to around 320 Kelvin, which is 47 degrees, showing a clear improvement in heat stability. From this, I found that 3D printing brings design freedom, but material limitations are significant. Magnetically, low flux density causes weak torque. Thermally, low conductivity and softening lead to deformation. But this analysis gave me data-driven direction for improvement. I realized that if we combine different materials, magnetic ion PLA plus carbon fiber layers, and add built-in cooling channels through topology optimization, we can create a much more stable design. This project was not only about making a motor, but about learning how materials, heat, and magnetism interact. I finally understood why 3D printed motors fail and how they can improve. However, the research support was withdrawn, which unfortunately prevented physical prototyping. I'm ready for the next step. If I get the necessary research support, I plan to actually to print the motor, test it with an all-drive controller, and compare the real performance to my simulation. I believe this research can lead to lightweight, customizable, and sustainable motors for the future robots, drones, and electrical vehicles. Thank you for listening.